Welcome to What is Mass Spectrometry? So mass spectrometry is an analytical technique for measuring the masses of atoms, molecules, and fragments of molecules. In general, we have some ions come in. We have to ionize molecules or fragments of molecules over here. When we pass them through some separating device, in this case it happens to be a magnetic field, as we pass those ions through, the lighter ions will be deflected farther, and that means that these blue ones are striking down here on our detector, and the red ones, the heavier ones, will be deflected less, so they may be striking up there on our detector. Now typically what we do is we scan through. We don't have a detector that's detecting all masses at the same time. We scan through and we are able to change the magnetic field here, so we have just a single mass that's striking our detector. So to record a mass spectrum, gaseous species that are desorbed from condensed phases are ionized. The ions are then accelerated by an electric field and separated by a mass-to-charge ratio mz. So if the charge on the ion is +1, then the mz is equal to the mass. If the charge on the ion is +2, then the mz is half of the mass. So the mass spectrum displays detector response as a function of mass-to-charge ratio. This mass spectrum here shows 4 peaks, one from each of 4 naturally occurring lead isotopes. The peak areas then correspond to the relative abundances of each isotope. In this chapter, we're going to use nominal mass to describe species, not the atomic or molecular mass. So the nominal mass of a molecule or ion is the integer mass of the species with the most abundant isotope of each constituent atom. A magnetic sector mass spectrometer, this is similar to the one that I showed on the first slide, uses a magnetic field to select only ions of 1 mass-to-charge ratio that are able to pass to the detector. So neutral molecules in the gas phase are ionized up here in our ion source, and then they're accelerated towards the analyzer tube by an electric field. So we've got our neutral molecules coming in. We've got a filament here that emits some electrons. Those electrons are used to ionize our molecules into ions. Those ions are then accelerated through some ion acceleration plates. They pass through some ion focus plates, and then they come out of our source. They travel down our drift tube here. In this case, we've got an electromagnet as the ions travel through that magnetic field. The lighter ions are deflected farther, which means they strike the top of the tube here. The heavier ions are deflected less. They'll strike the bottom of the tube. Only those ions that we're interested in this case the blue ones, will manage to travel down the analyzer tube, go past an exit slit, and strike our detector. So once our ions are in the analyzer tube, then the ions encounter that magnetic field that's perpendicular to their travel, and the tube has to remain at high vacuum, so this is around 10 to the -5 pascals or 10 to the -7 torr. In order that the ions don't interact with each other, the magnetic field then deflects the ions towards our detector over here, and we control the strength of the magnetic field such that the ions with our desired mass-to-charge ratio are deflected just enough to strike the detector, and ions with a lower mass-to-charge ratio are deflected too far and strike the tube wall, not our detector. Ions with a higher mass-to-charge ratio are not deflected far enough and strike the tube wall, not our detector. When an ion strikes the electron multiplier detector, then an avalanche of electrons is released, similar to the arrival of a photon at a photomultiplier tube. So you can see down here, as we have an ion come in and strike our cathode, then some electrons are emitted. They strike a dynode. That dynode emits additional electrons. Those electrons then strike a second dynode, and so on, multiplying the signal until those electrons eventually strike an anode. So while a mass spectrometer usually monitors positive ions, negative ions can also be analyzed by reversing the voltages where ions are formed and detected. A conversion dynode with a positive potential can capture the negative ions and then release positive ions. Those positive ions are then accelerated into the electron multiplier. So we use electron ionization to ionize neutral molecules entering the ion source up here. So current flows through a filament, heating it until the electrons are thermally emitted. Those electrons are then accelerated by about 70 volts and collide with our neutral molecules. And a fraction, so this is a very small fraction, only 0.01% or so, of our molecules in will absorb somewhere between 12 and 15 electron volts, which is enough for ionization. So we've got our molecule, neutral molecule, plus an electron at 70 eV. That reacts to give us our ion, plus the electron that now has lost about 15 eV, so now it's got about 55 eV, plus another electron that's been emitted with a very small amount of energy, around 0.1 eV. So remember that nearly all stable molecules have an even number of electrons, and that means that one electron is lost from our neutral molecule to form our ion. That resulting cation has one unpaired electron, and we denote that this way with that dot to indicate that it's a radical, and this is the molecular ion. So our molecular ion usually has enough internal energy, around 1 electron volt or so, to break into fragments. And then a small positive potential on our repeller plate, which is up here, pushes the ions towards the analyzer tube. Another small potential on the ion focus plates here forms the ions into a focused beam. And then a high voltage between the acceleration plates here and there. So this is somewhere between 1 and 10 kV. Causes the ions to move at high velocity out the bottom of the ion source and into our analyzer tube. Now, because the molecular ion may retain enough energy to break into fragments, then the parent peak, with our molecular ion intact, may be small or undetectable. For example, the mass spectrum of pentobarbital, you can see the pentobarbital structure over here. Pentobarbital has a nominal mass of 226, which would show up around there, and it doesn't show up. So we often compare the spectrum of an unknown with a library of known spectra via a computer search. The most intense peak in our spectrum is called the base peak, and in this case, it's going to be this peak at 141. All the peaks are expressed as a percentage of our base peak then. So our base peak is listed at a relative abundance of 100%, and all the other ones are less than that. And if we ionize with 70 electron volt electrons, then we make cations almost exclusively. But if we lower our electron energy, then we can create anions via two processes, via resonance capture and dissociative capture. So with resonance capture, we've got rather low energy electrons that are being captured by our neutral molecule to give us the anion, and again it's a radical, so we've got that dot there. We've got dissociative capture as well, where we have XY reacting with an electron to give us X plus Y minus, and again that Y minus is a radical. If we desire less fragmentation, then we can use chemical ionization instead of electron ionization. And in this case, the ion source is filled with a reagent gas at around 100 pascals, so this is around 1 torr. So methane, isobutane, and ammonia are often used. We're going to focus here on methane, but similar statements can be made about the other reagent gases. So electrons of around 100 to 200 electron volts can convert the methane into a variety of reactive products. So you can see we've got the methane reacting with an electron to give us the methane ion and 2 electrons. We can then have that ion react with another methane molecule to give us a CH5 plus ion and now a methyl radical. Note that this methyl radical will not be detected in our mass spectrometer because it's a neutral species. We can have our methane ion that we created up here split apart and give us a hydrogen radical and a CH3 group. We can then have that CH3 group react with another methane to give us C2H5 and hydrogen. So that CH5 plus ion is a proton donor that can react with our analyte to give MH plus, our protonated molecule. So we can get this MH plus, our protonated parent molecule. And our protonated molecule is generally the most common ion in our chemical ionization spectra. Here's an example of the chemical ionization of pentobarbital. Over here we've got the chemical ionization, and here we have the electron ionization. And you can see that when the methane is used to ionize the pentobarbital, this parent peak here at 227, remember the pentobarbital has a mass of 226, so when we add the hydrogen, we've got a mass of 227 now. That's going to be the second largest peak with the chemical ionization. Remember the 226 peak, that parent molecular ion peak, was not shown with the electron ionization. So note that the peak at 157 is likely due to the protonation of our strong 156 peak here seen in the electron ionization. So the mass spectra that we've examined thus far have been bar graphs generated by a computer. But the actual signal from our spectrometer looks more like this, where we have a continuum, and what we've shown thus far is when we've are combining the portions that are at each integer mass. That is, each peak has a width that limits how closely two peaks can be and still be resolved. If the peaks are closer, then they'll appear as a single peak to us. And the higher the resolving power of our spectrometer, then the greater the separation between our two peaks with similar mass. Now, the resolving power can be defined in a few different ways. The first way is this way, with the resolving power equal to m over delta m, where m is the smaller of our two mass-to-charge ratios, and delta m is the separation of our two peaks when the overlap of their base is 10% of the max peak height. Or we can define resolving power as m over m half, where again m is the smaller of our mass-to-charge ratios, and m half is the width of the peak at half max. This is the full width at half max. So in this case, m1 half is 0.481 Daltons. So that's this width here. So here we see the resolving power m over delta m equals 500, and we can clearly see a separation between those two peaks. Here we have the resolving power with those same two peaks, but now with our other definition, m over m1 half, we have a resolving power of 1040. If we use this definition and that resolving power of 500, we get this spectrum here, and you can see that these peaks are not very well resolved at all. So you must specify very clearly which definition you're using, whether you're using this definition or this one for your resolving power. So that was, what is mass spectrometry?